The 14 elements from thorium to lawrencium, in which the differentiating electron enters the 5f orbital, are called the actinoids. Only the first 3 elements, namely thorium, protactinium, and uranium, occur in nature. The other elements are made artificially by nuclear bombardment. All the actinoid elements are radioactive. The first few members have relatively long half-lives. However, the remaining members have half-lives ranging from a few days to a few minutes. Let's first look at the electronic configuration of these elements. The electronic configuration of actinoids is given in the table here. Since the difference in energy between the 5f and 6d orbitals is small for the first 4 elements, thorium, protactinium, uranium, and neptunium, the electrons in these elements and their ions may occupy the 5f or the 6d levels, or sometimes both. However, note that the filling of the f orbital starts only at protactinium and not at thorium. Later in the actinoid series, the 5f orbitals do become appreciably lower in energy. Thus, from plutonium onwards, the 5f shell fills in a regular way, and the elements become very similar. The irregularities in the configurations at curium and lawrencium are related to the stabilities associated with the half-filled and completely filled configurations. As 5f orbitals are not as deeply buried as 4f orbitals, the 5f electrons can participate in bonding to a greater extent. This explains the higher oxidation states shown by the earlier actinide elements. Now, let's look at the atomic and ionic radii of these elements. The atomic and ionic radii of the tripositive and tetrapositive actinoid ions are given in the table. As you can see, there is a steady decrease in the ionic sizes of the tripositive and tetrapositive ions. This may be referred to as actinoid contraction. Due to the poor shielding by the 5f electrons, the contraction is greater from one element to another in the series. Now, let's talk about the oxidation states of these elements. Unlike lanthanoids, actinoids show a variety of oxidation states. This is attributed to the small energy difference between the 5f, 6d, and 7s levels. The oxidation states of these elements are given in the table. You can see that +3 is the common oxidation state of actinoids. The maximum oxidation state first increases up to the middle of the series and then decreases. That is, it increases from +4 for thorium to +5, +6 and +7 for protactinium, uranium neptunium and plutonium, but decreases in the succeeding elements. Actinoids, like lanthanoids, have more compounds in the +3 state than in the +4 state. However, +3 and +4 ions in actinoids tend to hydrolyze. While lanthanoid ions do not.